Alrighty, let's wrap up general linear models. Um, so, as I've mentioned a couple of times, the terminology that a lot of times people use, like ANOVA and regression and multiple regression and stuff like that, really are doing more to convey the design of the study than they are actually the analysis. Because again, they're all linear models and they're all playing by the same rules, and everything is calculated in roughly the exact same way across all those different designs because we're doing it as a general linear model. And if we recall, we call it a general linear model because it's general, because it can accept both categorical and continuous predictors or covariates. And up to this point, we've played with models where it's either all continuous or where it's all categorical predictors. And so next, I just want to play around with some models where we have a mixture of both continuous and categorical predictors. And traditionally, this is what's referred to as an ANCOVA, which is analysis of covariance. But again, it's just a linear model, and we're going to do hypothesis testing on that linear model using analysis of variance. But the design is called an ANCOVA, and that's generally how people think about it. So let's take a look-see here real quickie. And I'm going to read in some data that we all have to play with called diet ANCOVA data. And let's take a look at what these data are. Okay, so these data are done with caterpillars, no surprise, because Jim likes caterpillars, so he happens to have that type of data. And here we have caterpillar weights after 2 days of feeding on a particular diet. And so for this scenario, what we are interested in is there are two possible diets that the caterpillars were feeding upon. So either diet A or diet B. Okay. And then we have, of course, the weight of the caterpillar, and that's the thing that we're interested in being able to make a model to predict. We'd like to be able to predict caterpillar weight. And so we have two different diets that we can think about, but we also kept track of diet consumed. And so you could imagine a situation where if you have a diet that is very nutritious, you might have a situation where the caterpillar consumed, or two different caterpillars consumed the same amount of food, but one of them might develop more than the other develops simply because one of the diets is superior. Likewise, diet consumed could be one of them tastes really good, so the caterpillar is just an extra hungry caterpillar and feeding that much more, which would result in it gaining weight. And then for our purposes here, we're also going to imagine that for each one of these experimental arenas that we had where we were rearing these caterpillars, we had some measure of the temperature within that arena. Caterpillars are ectothermic animals, and so the outside air temperature would affect their physiological rates, which might also affect how much weight that they might gain. So we have these data, and ultimately we're interested in predicting weight. Okay, so we could start with just a very simple model, like the models that we've played with already when we introduced ANOVA, meaning when we introduced the concept of having categorical predictors. And we could set up a simple linear model where we have weight being some function of diet, and then I will tell it that the data that I'm using for this is DAT. Okay, so it'll know where to look for weight and diet, and I could go ahead and I could run that, and now we have our model. We understand how to interpret these parameters. The intercept is going to be diet A because it is alphabetically the first factor level, and just by looking at these parameter estimates, we can see that on diet B, on average, those caterpillars weigh 1.612 less than on diet A, which is 7.152. And we could remind ourselves what it looks like behind the scene by using that model matrix function. Okay, and you can see everybody gets the intercept, so everybody starts out as a caterpillar that's on diet A, and then if you're on diet A, like these first number of rows are here, you would add 7.152 plus 0 times negative 1612. In other words, again, thinking about those ones and zeros as being switches. If you're on diet A, you're turning off the effect of diet B. Whereas if you're on diet B, which starts here at line 26, now you're going to start with the intercept, which is 7.152, and then you're going to subtract from that 1.612, and that would be your expected value. So we have that, and you know, we could do all of our old tricks. We could go ahead and do an ANOVA on that, and we could say, aha, they're different from one another. Case closed, right? But we also have the amount of diet consumed, and again, we want to use that as a covariate because we'd like to understand is it just simply that they're eating more of diet A versus B, or is there some kind of a relationship between how much they eat of either of those diets, and then is the difference between those two diets maintained? And so we can do that by simply adding to our model our continuous covariate, which is diet consumed. Okay, and so now we have an intercept again, we have the effect of diet B, and then we have the effect of diet consumed. So we have a positive slope for diet consumed. That means that the more you eat, the more you'll gain weight. That makes sense. And then similar to before, if you're on diet B, on average, you're simply going to weigh less than you do on diet A. And again, if we looked at the model matrix of this new model, you can see again, everybody starts with an intercept. Everybody has diet consumed, so everybody's going to be included in diet consumed. And then we have our toggle on-off switches with our dummy coding for whether or not you're on diet A or whether or not you're on diet B. And so let's go ahead and take a look at what we've done up to this point. So I'm simply going to plot our data. Okay, here's our data. And then to be cute, I am going to color code it. So I'm going to make it so that way if you're on diet A, you are going to be red. Okay. Again, all this code is in the code that is up on the canvases. Okay, so there's our data. We've color coded the different diets based upon how we've chosen to model it, like this. We have two different slopes now, right? We have a slope that's associated with diet A, and we have a slope that's associated with diet B. And so again, if we look at our model parameters, we can draw those AB lines now to go over this graph. So we could start with wanting to say plot diet A. And so we will say ab line what? A is going to equal 2.469. Right, that's our intercept. Everybody gets an intercept. And then the slope that's associated with it is that 1.295. Okay, and then to make sure that we're keeping track here, color equals red. And there's the line that's describing the effect of being on diet A. And then likewise, if we wanted to draw another line for individuals that were being reared on diet B, we would start out with the same stuff. Get rid of the color here. Okay, except here now the intercept is going to change, and the intercept is going to change because when you're on diet B, you're also including that, right? On average, on diet B, according to this model, you weigh 1.607 less than you would weigh on diet A. And so I'm going to go ahead and say 2.469 minus 1.607. The slope stays the same. Everybody has the same slope here. So I'll go ahead and do that. And now that is the line that's describing on diet B. And so if you notice, what's happening here is the slope of the lines are staying the same, but the elevation of the lines is different. And so this is, on average, the black line here is 1.607 less than the red line, no matter where you are on this red line. So you can have individuals that weigh a lot, that ate a lot, but you're always going to weigh less when you're on diet B compared to when you're on diet A. Okay, and this is formally what people usually refer to as an ANCOVA. And the reason why it's called analysis of covariance with this type of design is because you basically want to control for the effect of diet consumed, and then you want to ask whether or not the diets are different from one another once you've taken away the effect of how much the individuals have consumed. And so here I want to just do a quick little caveat, because sometimes people, I don't think maliciously get bad advice, but I think they naively get bad advice from people. And it shouldn't be an issue, because we've already talked about p-hacking and the fact that models are models and so on and so forth. But sometimes when people are like, there's just not quite that big of an effect, the p-value is 0.04 or whatever it might be. Or no, 0.051. Let's take something ridiculous like that. And so one strategy that sometimes people will advocate for is to run a model where you just have your covariate, diet consumed, and then save the residuals from that model. So here I'm going to create an object called regmod. It's a linear model where all I'm going to look at is weight and diet consumed. That's it. Okay, so I have that. And then I'm going to save the residuals from that model, which again is just all the leftover variation that diet consumed isn't able to explain. And what I'm going to do then is I'm going to create a new object, so that way R just knows what the heck I'm talking about, called diets. And diets is simply going to be what diet you're on. So I'm going to just extract it right from our big data matrix. So here's the different diets, right? And so I can run now a linear model on the residuals. Resid mod. It's a linear model where I will take my residuals and I will say they're some function of diets. And now we have our residual model. Okay. And we can compare that against the parameters of our big model, where we included them both. And notice that the overall effect of diet has stayed the same. And if we were to look at the residual model itself, right, we are getting the same slope that we got in the big model. And so then, and this is totally fine, because this is really what's happening behind the scenes of this model. If we're looking for the effect of, if we're looking to estimate a parameter for the effect of diet, we're going to partial out the effect of diet consumed and then estimate a parameter for diet. And likewise, if we're interested in diet consumed, we could have made a model where first we ask what is the difference between those two diets, save the residuals, and then make a model where diet consumed is predicting the residual weight that's left over. And all of this is fine. The parameter estimates are all the same, so that should make us feel good that we understand what's happening behind the scenes when we're doing an ANCOVA. But the problem comes is when we decide that we really want to analyze this model using an Anova. And so we do this, and it's like, okay, well, diets are significantly different. Let's compare that against our big model, where we included both. And what you'll see is that the sums of squares are the same, but what's different are these F values. And the F value for the residual model is actually slightly larger than the F value for our larger model. And that's because of how the F value is calculated. Remember that the F value is calculated as the ratio between the mean squared component of our effect and the residual mean squared. And the reason why we end up with a larger F value is because here the computer does not know that we already had to build a model to generate those residuals. The computer does not know that we're analyzing residuals. And so as a consequence of running a model, saving the residuals, and then analyzing those residuals, is that we're not accurately keeping track of degrees of freedom appropriately. This 47, that is the appropriate degrees of freedom that we should have for this particular model. 48 is failing to account for the fact that we had to already estimate a parameter to get those residuals. And this is why you simply should probably, except on very rare occurrences, unless you think about it really hard, you probably should never do an analysis of variance on a model that's based upon the residuals, based upon a model that's another subset of your predictors that you could potentially have in the model, because you're failing to keep track of degrees of freedom. Now you could by hand calculate the mean squared from this by dividing it by 47, and then if you calculated that F value, you would get the correct F value. So I just wanted to mention that because sometimes people get the bad advice of, and it's especially true if people are trying to encourage you to p-hack, which I am encouraging you to never consider p-hacking. But oftentimes people will get the advice, run the model, say the residuals, and then run the analysis on those residuals using some other part of the data. The model itself is fine because your parameter estimates will be consistent between the one large model and then doing it as a two-step type process. But your hypothesis testing will be wrong because you're inflating your error degrees of freedom. So I just wanted to mention that because it's a common piece of advice that people get, and we probably should not do that because we're failing to keep track of how many random variables we actually have. Okay, so let's go back to our model. Let's kill this caveat. The caveat is in the notes as well. And so we have this model, and if we look at our plot, you can see what we're assuming based upon this model is that the slopes are equal to one another, right? There's only one slope available. And this is what's referred to as additivity. Okay, so we are assuming that the slopes and the diet are additive, that there is an effect of diet and there is an effect of diet consumed, but we're assuming that the slopes are the same. What we want to do before we would feel good about that model is to make sure that that is a good assumption, because it's entirely possible that the slopes are actually different from one another. And so let's set up a model where we allow for an interaction term. And the interaction term will tell us whether or not we should feel comfortable about modeling this as being an additive type process. And so we can do that by saying diet times diet consumed. And so I'm going to go ahead and I'm going to run this, and this is going to tell R very kindly, would you please make a model where you are estimating an effective diet consumed, and the interaction term, meaning the potential non-additive component of the relationship between diet consumed as it pertains to weight. And so let's see here. Oops, that's not what I meant to do. So let's go ahead and we can run an ANOVA on, well, first let's do a matrix of the model just so we can see how it's dealing with this interaction term. Model matrix is probably the function I'm looking for. Okay. And so again, everybody consumes a diet. That's great. We understand what these ones and zeros are meaning here. That's the dummy coding. Everybody is getting an intercept. Only if you're on diet B do you get the effective diet B, so that's where that toggle switch gets turned on. Everybody gets a slope for diet consumed, but then if you are on diet B, you have this extra set of values that you are going to use to also think about the effect of diet consumed. Okay, and it's literally multiplying. Since it's diet times diet consumed, it's 1 times 5.6 equals 5.6, just like, 0 times 2.6 equals 0. And so this is what the model matrix looks like in the background, and this is what the computer is using when it's going to develop our model. So we can go ahead and we can analyze our model in anova.mod. And what do we have here? Well, the first thing that we want to look at when we have a model with an interaction term is how do we feel about that interaction term? And what we have here is we have a significant interaction term. So as soon as we have a significant interaction term, that is telling us, well, it's telling us two things. In principle, what it's telling us is that the slopes of those two lines as diet consumed, the effect of diet consumed on weight, that slope is different between the two different diets that we might be feeding on. The other important thing that we want to consider is that when we have that significant interaction term, we can no longer trust the hypothesis testing that has to do with diet or diet consumed. We can no longer trust that because if when we're testing those hypotheses as single factors by themselves, we are assuming additivity. This interaction term is telling us that there is no additivity. And so at this point, what we're going to need to do is understand what is driving that interaction term, okay? Now I will say that our model is fine. I love these parameter estimates. You know, I always advocate for loving your model. I love this model. I love it. And I'm totally happy with those parameter estimates. What I'm not happy with is the hypothesis testing part associated with those parameter estimates. And so what I'd want to do is I'd want to now split the model into two different models. I would want to have a model where I'm only looking at diet A, and I would want to have a model where I'm only looking at diet B. So that way I'm going to be able to do the hypothesis testing on the importance of diet consumed between both of those diets. And so I'm going to create a model A and a model B. And all I've done here is I'm just restricting the weight data to where diet is super duper equal to A and where diet consumed is super duper equal to A. And so I'm just going to do everything from here up, basically, in the raw data, okay? And so I'm going to go ahead and I'm going to make that model. I'm going to do the same thing for mod B. And now let's look at the parameter estimates for mod A. And we'll look at the parameter estimates for mod B. And then we'll go back and we'll revisit our original model, our big model with the interaction term. And so what we can start with is thinking about how these parameter estimates are all kind of going together, right? So this is the model for A right here. And here we have our intercept as being negative 0.5747. And that's the same intercept we got in our really big model, okay? Because it's the first it's the first factor level. And so everyone's going to start out as a caterpillar who is on diet A, right? And so that's where our intercept is going to be. Looking at our big model, we can think about where does this 2.9508 come from? And that is going to be the difference on average between the expected value, the intercept for A, and the intercept for B. And so if I were to use this built-in function in R called diff, which will give me the difference between two values, I can just go ahead and I can pop those values in there. So it's going to be negative 0.547, and it's going to be 2.3768, or 61, I guess, whatever it is. Is that what I'm saying here? Yes, that's what I'm saying here. So I go ahead and I run that, and I get, did I miss that number? I did. I get the difference between those two is the same as the effective diet B in the big model. So the intercepts between the two separate models are still retaining what is the overall average difference between diet A and diet B, except here it's all in one model, and here we're just interpreting it as two different intercepts, but the difference between those two intercepts does capture what the overall effect of diet B is. So next, let's think about the slopes. And so if we compare the slope for our model B to our overall, to that interaction term right there. So if I were to take, well, let's start with, if I were to take 2.1368, so that's the effective diet consumed, and then I'm going to add to that negative 1.2609. That is the parameter that's associated with the interaction term. I get 0.8759, which is the exact same slope that I got when I just modeled diet B by itself. So this interaction term here is telling you how different the slope is if you're on diet B compared to if you're on diet A. If you're on diet A, that's your slope. If you're on diet B, your slope is that much less than if you were on diet, or I'm sorry, if you were on diet A. And so let's go ahead and we can now plot this. Well, first of all, I guess what we should do is, since we split the model into two different things to understand the interaction term, we should probably go ahead and we can analyze that. An ANOVA on model A, and then an ANOVA on model B. Okay? Both times the slopes are significant, but the slopes are different. And we can think about how different those slopes are just by looking at our full model parameters. Because again, our full model parameters are great. I love our full model. I just didn't feel very good about the hypothesis testing part. And so when you have that significant interaction term, if you want to understand what's driving that for the sake of communicating p-values, or just to make any kind of deductive statistical inference, you have to then dive back into the model and explore what is driving those interaction terms. And it's pretty clear what's driving those interaction terms is that the slopes are pretty different between diet A and diet B as it relates to the amount of diet consumed. And so let's think about how we might plot these, because we always want to be able to make a pretty plot. People love pretty plots. I love pretty plots. You should too. So I'm going to say plot weight is some function of diet consumed, and the data that we're playing with is that. And I should probably make this big enough so I don't get that error message. That's helpful. Okay, so here's all of our data. And now what I'm going to do is I'm going to color code our points again. I'm going to make diet A red and diet B blue, just because, again, the goal here is a really pretty plot. Okay, so here's our two different diets. Just by eyeballing this, we can see that, well, the more you eat, the more you weigh. But it certainly does look that, on average, diet A, the red diet, you're weighing more than if you're on diet B. And so let's go ahead and we can plot the lines for each of those on here from both of our models. And now you can really see why that interaction term is important, okay? Because, yes, on average, the red diet is bigger or weighs more than on the blue diet, on diet B. But you can see that when caterpillars are feeding on very, very little, that there's really no difference between those diets. It's only once they start consuming a moderate amount of diet that you start to see this spread in the performance of those caterpillars between those two diets. And so that's what we can learn from that interaction term. It's telling us that it's not purely additive. And if we remind ourselves when we did it as an additive model, it looked like that, right? But here we were modeling it as having identical slopes, whereas now we are modeling it and we're allowing the slopes to differ between diet A and diet B. And so visually, that's a really nice way to show it. If this were like a paper, for example, you would run the ANOVA, you could communicate the ANOVA, show that there's a significant interaction term, and then say, to understand what was driving the interaction term, we did subsequent ANOVAs on only model on diet A and only diet B. And we can see what the power is of this type of an approach because we're including a lot more information in the model. If we had just done a linear model where we had only put diet consumed in there and ignored the different diets, that line would look something, nope, that's not what I meant to do. Oh. Yeah. That black line there, the dotted black line, that's if we had ignored the different diets and we were just trying to model diet consumed, if we didn't have any information about the different types of diets. But because we put more information in there, because we know if they were feeding on either diet A or diet B, we can understand how the amount of diet consumed influences how much the caterpillar should weigh depending on what diet it's on, and of course the how diet consumed affects the weight based upon what diet the caterpillars are reared on. And this is all an ANCOVA is. It's just simply a general linear model where you have both continuous and you have categorical predictors. Okay, so if you go back to our data, let's just play really quickly with one last thing here, just to run through what an exercise might look like. Froze up, so I'm starting where I froze up. So if we go back to our original data, remember that we also had temperature that we were interested in thinking might be, where did I go? Look at Jim hiding. What's that little fella doing? Where's that little fella going? There, okay, now I won't leave. We have here temperature as potential covariate, and so we might want to include that in the model. So now this is really where we would probably have started, right? Because up to this point, we've started at a very simple model and progressively made it more complicated. But we mainly did that so that we could understand what was happening in these models. If you had all this data, probably what you would do, the first thing is you would just dump everything in the model and see what the model looks like and maybe do some model selection. So let's create a new model. Oops, yelling at me. Let's create a new model where it's going to be a linear model where we are going to predict weight as being some function of diet, and then we will include diet consumed, and we will include temperature. Data equals dat. Okay, so setting it up this way, what this is telling R is that we want to look at all the possible interactions, including in this case a three-way interaction, where you're looking for a non-additive effect if you include both diet consumed, and temperature. Okay, and so we can go ahead and do that. The other way we could have set up that same model is to have done pluses there, but then in parentheses tell the whole model that we want to go up to the three-way interactions. So again, if we do that, there's our parameter estimates from the model. If we set it up this way, we get the exact same parameter estimates for the model. And this little thing up here, kind of limiting the number of interactions that you have, can be pretty handy when maybe if you have like 5 things in the model and you're like, there's no way I'm going to even understand what the heck a 5-way interaction is, and you want to restrict it to say 2-way interactions, you could just do that, and then it won't explore anything above 2-way interactions, so there won't be any 3-way interactions. But let's start with a 3-way interaction. So we have our model again. If we wanted to, we could look at our model matrix just to make sure we understand what's happening behind the scenes. Let me make this a little bit more like this, and then make this a little bit more like this. And now our model matrix is getting bigger. But again, everybody's going to get an intercept. Diet B is going to get, or diet A is going to get certain things or not get certain things that diet B does, because diet A will not get that coefficient involved with diet B. And then these interaction terms are quite literally multiplying these different things together. So 0 times 3.6 is 0. 0 times 25.0 is 0. 3.6 times 25.0 is going to be 90. And then 3.6 times 25 times 0 is going to be 0. So our model matrix is being calculated the same way as before. This is what's happening behind the scenes in the computer. And so we could go ahead and we could run an ANOVA on our big fat model. And we can eyeball that and say, well, okay, there's no 3-way interaction because those are really tricky to interpret. There doesn't seem to be any diet consumed by temperature interaction. That's nice. That's additive. Diet by temperature interaction. That's nice. It means it's additive. Here again is our interaction term between diet and diet consumed. Temperature doesn't appear to be significant, and then diet and diet consumed appear to be significant. But again, we have an interaction term, so we have to deal with the fact that we have that interaction term. And so the first thing we might want to do is just make this model simpler, right? Because we're eating up degrees of freedom to estimate parameters we clearly probably do not need to estimate. I mean, this 3-way interaction term, we probably don't need to estimate a parameter for that because it's not even, close to being interesting on the level of significance. And it seems like for hypothesis testing, all it's really doing is eating up degrees of freedom. And for parameter estimates, all it's doing is eating up degrees of freedom, which means that the more parameters we have in the model, the greater the uncertainty around those parameter estimates. So let's go ahead and do a little bit of model selection, and we can use that step function as we have in the past. And it's going to go through, and it is going to settle on this being the best model. Okay, so a model that includes diet consumed, temperature, and a diet by diet consumed interaction term. And so let's go ahead and run that model that they suggest for us to run. I'm going to call it final mod. It's a linear model that looks like that. The data equals dat. This colon here, that has the same effect as an asterisk. So that's just another way, if you want to write it out longhand, what you want the interactions to be, you would use the colon. And so let's, here we have our final model, blah, 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 all happy. There we have it. Okay, here's the parameter estimates of our final model. We could run an ANOVA on that final model. And again, temperature doesn't appear to be significant, but it wants to it wants to include temperature in the model. You would probably be justified to say I'm not going to include temperature in the model because the slope isn't significant, and I'm really interested in doing hypothesis testing on my parameters. But to play it conservative, we'll follow the step function, and this would be our final model that we would communicate to people. And then again, because we have this significant interaction term, we would again want to split it between diet A and diet B, including temperature in both of them, but diet A and diet B, just like we had done before for the purposes of hypothesis testing. But our parameter estimates alone, we totally believe that is the best model based upon the information that we have here. That is the best way in which we can predict caterpillar weight, is to pop the data into this model with these parameter estimates, and we will get the expected weight given whatever the temperature is and whatever the diet consumed is and whatever diet they happen to be on. Okay, and so so that is the wonderful world of ANCOVA. Again, ANCOVA is pretty much just describing an experimental design where you have continuous covariates as well as categorical covariates. But it's just a general linear model that we feel good about analyzing with an ANOVA because we already know how an ANOVA works and we know how a linear model works. So it's kind of a piece of cake, as it might be, hopefully. So play around with that, and yeah, and so that's the end of the ANCOVA part, and we'll finish it up with the factorial part. Let's finish up the our last little introduction here to just general linear models as we've been talking about them, and think about what is referred to as a factorial ANOVA. And I know I've said it before and I'll say it again. They're all linear models. They're all doing the same thing behind the scenes. Factorial ANOVA is really referring to an experimental design rather than referring to the type of analyses done, okay? And so what is a factorial design? A factorial design is where you have more than one categorical predictor in the model. And a pure factorial design is you have more than one categorical predictor in the model and you have no continuous covariates. But as we'll see, it's really not that how we're going to play with it. It's not that different from an ANCOVA. And so I'm going to just cook up a play data set for us to play with here, thinking about a factorial ANOVA. Let's assume that we have three different treatments, which I will cleverly refer to as A, B, and C, okay? And then let's stick with the temperature theme because we were playing around with temperature, but instead of temperature being a continuous covariate here, let's say that we have either high temperature or we have low temperature, okay? And then that means that if it's a factorial design, our experiment will include all possible combinations. okay? And for the experiment that we're going to play with here, when we simulate the data, we're going to just say that n equals 5 for all of these different combinations, okay? So everything is crossed with everything else. So it's a crossed design, which is also called analyzed with a factorial ANOVA, but a factorial ANOVA is really just describing a cross design, okay? So we're going to just set something up that looks like that, because it'll be fun. Let me find myself, make myself small. Get small, smaller. There we have it. Okay, so in the code that you all have, I am basically simulating data, right? So I'm going to create a vector called treats, where I'm going to have 10 replicates in treatment A, I'm going to have 10 replicates in treatment B, and 10 replicates in treatment C. So it might look something like that. There's my 3 levels, A, B, and C. And then I will also have temperature, high and low, like that. And then because I'm going to set the seed, I know exactly what the answer is going to be, and you guys will all get the exact same answer. I'm going to just simulate some data. And then let's just take a look at the data. This is what it would look like if you put it into an Excel spreadsheet where you have your different treatments. Treatment A has both a high and a low treatment. Treatment B has both a high and a low. And treatment C has a high and a low. And then here over here is just simply our response variables. Okay. And so we could start, you know, kind of how we did when we were playing around with ANCOVA. And we could start with just a simple additive model where we're going to say mass is predicted by some linear combination of treatment and temperature. And we could go ahead and do an ANOVA on that model. And what we would conclude is that treatments appear to be important. Temperature does not appear to be terribly important based upon null hypothesis testing. And we could take a closer look at what we're looking at with this. I'm going to make a box plot. I'm going to make a box plot like so. Okay, box plot set up as a formula. Mass is some function of treatments and temperature. So I go ahead and I do that. And here we can see here are the high temperature treatments. Here are the low temperature treatments. And when we're doing the hypothesis testing part up in our ANOVA model here, what the means that we are comparing are simply the mean of the high versus the mean of the low. And so you eyeball that, and on average, it looks like there's no real difference between high temperatures and low temperatures. I could reorder this box plot just for graphical purposes. Plus treats. Okay, so now I have treatment A over here, high and low, treatment B over here, high and low, treatment C over here, high and low. The only difference between these two plots is I've just shuffled around the order at which the boxes are being drawn. And now we could think about, well, what's driving this no significant effect of temperature? Well, or I'm sorry, or what is driving the significant effect of treatment? And the significant effect of treatment is because the mean of treatment A is there, the mean of treatment B is there, and the mean of treatment C is there. Okay, so that makes sense why our ANOVA is detecting a difference among treatments, but not among or not between temperatures. And that's all fine, but what we're doing here is we are assuming that the effect of temperature and the effect of treatment is additive. And so to test whether or not that assumption is a good assumption, we need to include a model where we have an interaction term, right? Because the interaction term we can think of almost as a quality control step to make sure that we can interpret the hypothesis testing of our main effects. And so let's go ahead and we will run this. This is the exact same as if I had typed this. Okay. These are both the exact same thing. There's two different ways that we can do it in R. Okay. So we have our model. We could go ahead and we could do an ANOVA on our model. And here we have treats, again, yep, significant. Temperature, nope, temperature is not significant. But we have this significant interaction term. And as soon as we have that significant interaction term, just like with an ANCOVA, we can no longer interpret the hypothesis testing done via the ANOVA on what are often referred to as our main effects, right? So here's our main effects as treatment and temperature, and then we have this interaction effect. We have a significant interaction term, which means that we really do not feel good about trusting either of these hypothesis tests, these p-values. And so what might be then driving that interaction term? And so we can determine what's driving this interaction term by using what's called an interaction plot. And interaction plots are a way that we can simultaneously plot two different factors and our response variable on the same plot. And so let's just look at one, and then I think it'll be intuitive as to how to interpret interaction plots. And it turns out that there's a nice little built-in function called interaction plot. How about that? An interaction plot's going to want three things. It's going to want what's referred to as the X factor, which sounds super extreme, X factor. And for our purposes now, let's just say, fine, temperature. And what that means is that temperature is going to be on the x-axis. The next thing that we're going to want to include is what's called trace factor. Trace factor refers to the factor that we're going to want to make different lines for, whether or not, and here what we're going to do is we're going to say that the treats, are going to be our trace factor. So we're going to draw three different lines at high and low temperatures for each of those three different treatments. And then the last thing that we have to give interaction plot function is the response. And our response is going to be our response from our linear model. It's the thing we're trying to predict, which is mass. So I go ahead and I do that, and this is what an interaction plot looks like. And so by just eyeballing this, it's not terribly surprising that we have a significant interaction term, because at a high temperature, the difference between the treatments seems to be much larger than the difference between the treatments at the low temperature. Okay? And so going back to this ANOVA table here, trying to understand why maybe temperatures are not different from one another according to the ANOVA hypothesis test, that's because at that level of the ANOVA, we are comparing high versus low. And just by eyeballing those dots, they look like they're pretty similar to one another. Okay? And so just as we did with an ANCOVA, once we have that significant interaction term, that's telling us we need to dig in and interpret the hypothesis testing and understand what's driving that significant interaction term. And so what I'm going to do is I'm going to create two different models, one for high temperature and one for low temperature. So here's the one at high temperature. I'm going to only keep the masses that are at the high temperature, and I'm only going to keep the treatments the treatments that are at the high temperature. At this point, temperature is not going to be in the model, because for this model, there's only high temperature data. And then we're going to run another model, which is going to only be the low temperature data. So I'll go ahead and I'll run that high mod, and then I'll run an ANOVA on it. High mod. And okay, well, it looks like there is a difference among the treatments at the high temperature. Okay? And then obviously what you would do then at this point is you could do something like a Tukey's test to see where those important differences are, to see whether or not they're all different from one another, or if there's two that are not different from each other but different from a third. We could just jump in and do the same kind of post hoc test that we did when we were just playing around with simpler ANOVAs. So let's do the exact same thing for the low mod. Okay, so now we are only going to look at low temperatures. We're going to set up a linear model, and let's do an ANOVA on that. And now, treatment is not significant. Okay? That is one of the things that is driving this, or that's what's driving this interaction term, which is why we can't trust the hypothesis testing, or it's an illustration of why we can't trust the hypothesis testing for our main effects. Because if we had looked at this model and ignored the fact that we have a significant interaction term, we would have said, oh, well, treatments are important, temperature isn't. But when we split it into two separate models, because we have this significant interaction term, what we find is at high temperatures, there is something interesting happening among those treatments. But at low temperatures, we're failing to find something interesting at low temperatures. So we would be wrong saying that treatments are always important, because here, statistically speaking, hypothesis testing, it doesn't look like treatments are all that important if you're at a low temperature, but they are important if you're at a high temperature. And again, that means that temperature must be important, right? But again, we lose that if we interpret the hypothesis testing part of our full model. So let's do the same thing, but let's, instead of looking at this interaction plot, let's switch them around so that on the x-axis, we'll put treats, and on the y, and then for the trace factor, we'll put temperature. We'll keep response the same. All right, let's try this again. The interaction plot, where we're going to say that the x factor is going to be treatments again, the trace factor is going to be temperature, and the response is going to be mass. My computer froze again. Soon we will be modeling the probability that Jim throws his computer against the wall. Okay, so the same data, we're just going to arrange it differently, where our trace factor now is going to be the different temperatures. So let's go ahead and run that. And here again, we can identify, this is the expected if you're at a high temperature on treatment C. This is the expected if you're at a low temperature treatment C, and so on and so forth. Because we have that significant interaction term, well, first let's go ahead and look at why we might have gotten the statistical results we got when we ran the ANOVA. Let's run that ANOVA again so I don't have to scroll up. And here we have our significant interaction term, so that's motivating us to understand what's driving that. And then we have a significant difference among treatments. And the reason why we might have a significant difference among treatments is, well, here's the mean for treatment A, here's the mean for treatment B, here's the mean for treatment C, okay? And we're kind of ignoring the effect of temperature, we're just taking the overall mean, and that's the comparison that's being done up here with the treatment section. And so, okay, well, because we have that significant interaction, what we probably would want to do then is dig in a little deeper, right? So let's do a linear model where we're only looking within treatment A, and that means we're only comparing high temperature versus low temperature within treatment A. So I'll go ahead and I'll do that. Okay, within treatment A, there is indeed no effect of temperature. That is consistent with what our big ANOVA was telling us. So let's go ahead and we'll do the exact same thing for treatment B. So I'm just going to cut and paste a little bit, do some typies, rename this. Okay, do that. Okay, treatment B, there doesn't seem to be any real effect of temperature. So now let's go to treatment C. We run that, and there's the culprit, okay? This is the thing that was probably driving our significant interaction term. Again, if we were to go back to our big ANOVA, we fail to find an effect of temperature. We do find an effect of treatment, but we have this significant interaction term. If we did not further explore, just like when we did it the other way, when it was set around the other way, we would be wrong assuming that there is no effect of temperature, because indeed in treatment A, temperature, you're failing to detect an effect of temperature in treatment A. You're failing to detect an effect of temperature in treatment B. But in treatment C, there is an effect of temperature. And this is where it would be problematic if we just ignored the interaction term and went ahead and interpreted our main effects, because we would be wrong by saying that, we failed to define an effect of temperature. Actually, temperature appears to potentially be important, but only in treatment C, not in treatment A or not in treatment B. And so, we'd want to do that whole splitting up of the model, and then we would want to, and then that's the information that we would convey to the people that we were communicating to about our study. We'd say, well, we ran this big model, we got a significant interaction term, and so we did subsequent ANOVAs to understand what was driving that significant interaction term. And when you're in that situation, even if the interaction term isn't significant, interaction plots themselves are a really nice way to graphically show these types of data, because these lines in between here draw your eye to them. And so, you know, obviously if this is going to be in a poster or in a presentation or a paper, you'd probably want to make a prettier model, but that interaction plot function is a nice first step to kind of look and see what the pattern of your data might look like. So, okay. So let's revisit the model. So even though the hypothesis testing part, right, and how many times have I said this now? I'm starting to repeat myself, getting old. Even though we don't trust the hypothesis testing part of this ANOVA at all, right, because of that significant interaction term, that doesn't mean our model is bad. Our model is actually absolutely fine and dandy. I love our model. Gotta love our model, right? And we have these parameter estimates from our model, right? And we know that if we were to look at the model matrix, model.matrix, we could see what the dummy coding looks like for this big model. Okay. And again, just like before, everybody gets the intercept. So everybody's going to start off as somebody who's in treatment A at high temperature. And then we have all these little ones and zeros, and we can interpret, you know, these are our dummies. No offense to it, once again. But we can think about these as switches being turned on and off. So this first individual here, okay, that is an individual that's treatment A at a high temperature. So it's going to get the intercept, but then all of the other parameters in that model are going to be multiplied by 0. So again, we can think of them as switches, and we've just turned off all of those parameters that are in our interaction model. Where is that interaction model? What did I call that thing? Why did I call it that? Jim, what are you doing? Okay. There's our parameters. And so what I mean by our model being fine, even though the hypothesis testing part isn't, our model will predict the mean for all of those different combinations of groups. So if we were to start out with setting this up as the linear model that it is, it would look something like this, right? Here's all of our parameters. Everybody gets the intercept, so it's going to start at 1. Okay, and so this is going to be, let's say that we're trying to predict if you're on treatment A and high temperature. Okay, well, if you're in treatment A at high temperature, which again was, that kills me every time it does that, which again was this first row here. So all of the dummies are 0, everybody gets the intercept. And so that means that it's going to get the intercept, but it's not going to get any of these other parameters. Again, you can think of the zeros as being off switches. So we do that, we get 18.8951. Well, that means that if we were to take the mean of individuals in treatment A and at a high temperature, we get the exact same answer. See, our model is actually working. That's pretty cool. So let's just do another one, kind of playing around with the dummy coding and how it works. Let's just say, let's pretend that you're in treatment B at a high temperature. So we can go back, let's take our default model, because everyone is going to start off as an individual in treatment A at a low temperature, but now, or at a high temperature. Whereas now I want to know what's the expected value if you are in treatment B at a high temperature. So the toggle switch that I would turn on is the one that is associated with the slope for being in treatment B. So I would turn that on. This is for treatment C, so I would keep this one off. This is at temperature low, so I would keep that switch off. And both the interactions have to do with low temperatures, so both of those are turned off. And so that is the expected value that I have if I am in treatment B at a high temperature. And sure enough, that is the mean for individuals that are in treatment B at a high temperature. And so once you have your parameter estimates and you understand how to read the model matrix, you can come up with the expected values for any given combination. So I'm going to do just one last one. I think all of the permutations of this are in the notes that I gave you guys. I'm just going to walk through one more, and I'm going to think about what is the expected value if you're in treatment C at a low temperature. Okay, so let's go back to our default model. Let's turn all the switches off. So I'll go back to this model, starting just with the intercept. And now let's think about these parameters. Well, this is the parameter for treatment B, so I'm going to leave that parameter off. The dummy coding is going to be a 0. It's going to be turned off. This is the parameter for treatment C. Hey, we're in treatment C, so I'm going to turn that parameter on. Okay. Next, we have an effect for being at a low temperature. Well, we are talking about treatment C at a low temperature, so we're going to turn that switch on. Okay. The next parameter here is if you're in treatment B at a low temperature. Well, that's not the case here, so I'm going to leave that switch off. And then finally, we have a parameter for if you're in treatment C at a low temperature. Hey, that's what we're doing, right? We want the expected value for treatment C at a low temperature. So we're going to go ahead and we're going to turn that on. Okay, so we flipped on and off the switches. We go ahead and we run that. That is the expected value according to the model that we have. And we can go ahead and ask R to calculate what is the actual mean for treatments equal to C and temperature equal to low. And lo and behold, it's the exact same value that we got from our linear model. So that's always an important thing to remember, that just because you can't interpret the p-values in your analysis of variance on the model, your model parameter estimates themselves are absolutely fine. It's a really nice predictive model, potentially, or at least it's the best predictive model that we have based upon all the information on hand. And again, like, understanding how these model matrices work are important, because when you explore kind of higher statistical methods like doing linear modeling in a Bayesian framework, oftentimes those softwares will ask you for the model matrix. They won't do it for you behind the scenes like the LM function does, because the LM function is just trying to be nice to everyone. So, okay, so that's our model. That is what was driving. We've talked about what was driving the significant interaction term, what to do when you have a significant interaction term, and very important, how to interpret the parameters of this factorial design ANOVA. Okay. And so, last thing that I want to talk about is thinking about those interaction plots, and why, if you understand what the interaction terms are telling you, if I were to show you an interaction plot, in principle, you should be able to come up with a pretty good guess as to what things might look like they're significant, what things might not look like they're significant, but also be able to eyeball it and say, I would be really shocked if there wasn't a significant interaction term. So I'm going to use our same story problem with high and low and 3 different treatments, but this is just going to be a cartoon so that we can think about how do we interpret those interaction plots. And interaction plots invariably will be on the final exam, and you'll be expected to know, or at least come up with your best guess as to whether or not the treatment would be significant, or the other treatment would be significant, or whether the interaction would be significant. So I'm going to just go ahead and make a plot here. So we have high and low temperature, and then I'm going to have 3 different treatments that are crossed with that are red, blue, and dark green. Okay? And so just eyeballing this, I'm going to guess that treatments are not going to be significant, temperature is not going to be significant, but the interaction term is going to be significant. Okay? So that's that is what my expectation would be in this. And so let's first think about, why don't I think temperature would be significant? Well, the mean at high temperature is there. The mean at the low temperature is there. Just by eyeballing those, right? They look like they're pretty similar. So it would make sense that temperature would pop out as being not significant. So let's understand now why maybe treatments aren't going to be significant. So I'm going to go ahead and draw this exact same thing. And now what I want to focus on are, what is the mean of treatment A? Well, the mean of treatment A is there. The mean of treatment B is there. And the mean of treatment C is there. And so that's why we would expect, like, okay, we would not detect a difference among treatments. Likewise, we would not detect any evidence of any evidence of effective temperature. But we would expect a significant interaction term, and that's just simply because, just eyeballing this interaction plot, the blue treatment is really low at a high temperature and really high at a low temperature. The red treatment is really high at a high temperature, and really low at a low temperature. And then it looks like treatment C, the B, the green one here, C, it looks like temperature doesn't matter. And so again, that's telling you that you can't trust the hypothesis testing on those main effects, because something is clearly going on, and you can really eyeball it just by looking at these interaction plots. And so let's look at one more play example. Let's say that it looks something like this, and what the expectation might be. So if I were to look at this, I would guess that treatments would probably be significant, temperature probably not significant, and the interaction would be significant. And so why do I think that? Well, first let's think about temperature. The mean at the high temperature is what? It is there. The mean at the low temperature is there. So it makes sense that an ANOVA on that full model would fail to detect an effect of temperature. And then likewise, let's think about it among the treatments, okay? And I said that I thought that the treatments might end up being significant. Well, why is that? Well, the mean of treatment A is there. Get out of the way, Jim. The mean of treatment A is there. The mean of treatment B is down there, the blue one, and the mean of treatment C is there. And so clearly those means look like they're different. If you just lump together high and low temperatures, here we're only thinking about, the effect of the treatments. That's why it would make sense to me that, okay, it would make sense that treatments would come up being significant, but temperature would end up being not significant. And I also guessed, accurately, probably, that the interaction term would be significant. And the reason why the interaction term would be significant is, check out what's happening at the low temperatures here. At the low temperatures, there's no difference between the treatments. Whereas at the high temperatures, there's a large difference among the treatments. Okay? And so again, if this were our ANOVA results, where we had significant treatments, not significant temperature, and a significant interaction term, we should not in any way feel comfortable interpreting the statistical significance of our treatments, because they're probably only different at high temperature, and once you get to low temperature, there's no difference among those. Okay? And so those are just different ways. You should be prepared to be able to look at these types of interaction plots. And in the notes that I handed out, I have different examples of what these things might look like here. Okay? So again, this is the one we were playing with, where I would expect treatments and temperature to not be significant but have a significant interaction term. Here's the other one that we played with, where treatments would be significant, temperature not significant but a significant interaction term. But here's some examples where there is not significant interaction terms. So here, the treatments would be different from one another, okay? But temperature doesn't seem to be, and I wouldn't expect there to be an interaction term. So this is an example of where we only have a true effect of treatment, and we wouldn't have to further break up the model to do hypothesis testing. We would feel good about that. And then here's an example of where both treatment and temperature would be significant, but the interaction term isn't. And this is what's meant by additivity. Notice that each treatment has its own mean, right? Whatever treatment this is up here, it does really well, and this one does mediocre, and this one does poorly, okay? And then the temperature, it looks like overall, high temperature is always a little bit lower than the low temperature is, but that effect is consistent across the treatments, and that's what we mean by additive. There's an overall effective temperature, there's an overall effective treatment, and it seems to be consistent regardless of what combinations we're dealing with. And so this is where we would expect a not significant interaction term. I'll see, maybe I can remake these color, and I'll put them in the notes that are handed out with that. But guess what? That's the end of linear models, right? I mean, we just started linear models not too long ago, and we're done with all of linear models, which has encompassed everything that we think about with regression-y, multiple regression, ANOVA, ANCOVA, Factorial ANOVA, but now we know that all they are is linear models. And so play around with the linear models. And what we will do next time is we're going to start making the linear models a little bit more maybe complicated. But what we're going to do is we're going to revisit the error structure. Up to now, we've been ignoring the error structure. And what we're going to do next time is we are going to start putting structure to our error term. And that is going to be what's going to be referred to as a general linear mixed model, also known as a random effects model. But we'll do that next week. This week, let's just play around with ANCOVA and Factorial ANOVA. Let's just play around with linear models, and we'll ANOVA away. See you next time.